Alright, we're Design Team 5. I'm Joshua Myers, this is Ryan Lederach, Steve England, and Ken Giono, and our topic is current sensing with resistive shunts. So first I want to start with a quick outline of our presentation. I'm going to talk about what current sensing is exactly and some of the common applications of it. Ryan is going to talk about some common methods of current sensing. Steve is going to talk about high and low side resistive sensing. And Kenji is going to talk about some of the challenges of resistive sensing. Alright, so current sensing is simply a method of determining how much current is being drawn to load. However, the name current sensing is slightly misleading as you don't actually sense a current most of the time. So for example, you can sense a voltage that's dropped across a resistor and use Ohm's law to determine the current. Or you can sense a magnetic field that's going through a toroid and then find the current from that. And one challenge in current sensing is that there's a large range of measurements all the way from microamps to kiloamps. And depending on where you are in that range of measurements, you have to determine what technique you're going to use. So for example, if you're in the micro to milliamp range, you may have to use resistive sensing. Or if you're in the higher amp range, you may have to use Hall effect sensing or current transformers. Okay, here are some common applications of current sensing. So first is overcurrent protection, which is actually what what our project is based on. Basically, it's pretty self-explanatory. You sense a current, and if it's over a certain threshold current, you'll have some internal circuitry which will disconnect power to the load and keep an excess amount of current from going into the circuit. So this obviously helps prevent equipment failure and helps ensure the safety of the people operating the equipment. And of course, and then next is performance monitoring. If you obviously know the input to a system, how much current is being drawn, you can determine if there's any waste in the system, and you can improve the throughput of the system. And then power consumption is actually another project that we're working on, which is we are basically using ECE480 to determine how much current is being drawn from the system and then output it to a LED screen. So if you know how much current is being drawn in the system, you can improve the efficiency, and it can be useful in determining trend analysis for the system that you're working on. So next is Ryan on some common methods of current sensing.
Hi, my name is Ryan Lederach, and we're going to start with the Hall effect current sensing method, in which when you have a current going down a trace or a line, it's going to produce some kind of magnetic field. The magnetic field would be sensed or would be picked up in a toroid that is connected to a separate part of the circuit, and a special IC would then measure this induced voltage in this toroid, and from there you can determine the current sent through the line. The advantage of this is it can handle high currents, and because of it is connected to a separate circuit, there really isn't a insertion loss, but also it has a large size due to having a toroid and is a little bit more expensive than the other methods. And next we have the current transformer sensing, in which you have transformers, a transformer somewhere in the circuit, normally before the load, in which you have two inductors coupling, and from there you can determine the current going through the circuit. The advantages of this is, again, there's no offset voltage, and because it is a transformer, there is no external power required. And again, with disadvantages, because you're using inductors, it is a large size. It has a larger size than most other things. It's expensive, and it requires AC current to actually sense the current going through. And now we're on to resistive shunt current sensing, which is the one we're using. And this one is more simple. It's it uses Ohm's law with having a small resistance, and you have a voltage drop across that. And there's a special IC, or there are ICs that measure this voltage drop. The ICs can be anything from an instrumentation amplifier to current shunt monitor, or even a simple op amp. And all it does is it amplifies the voltage drop and outputs a known voltage for any current or any voltage that it senses. And the resistive shunt can be either high side or low side. Advantages are it's a lot quicker than the other methods we were looking at. It's a lot smaller than the other method because of it's just a resistor and some ICs. And the accuracy is a lot better. Disadvantages is because you have multiple ICs, there is an insertion loss, and that it only handles low current, which is normally microamp, to somewhere in the amp range. You can't handle anything higher. And next is Steve with high side and low side measurements, or current sensing.
I'm Stephen England, and I'm going to talk a little bit about high side and low side current shunt measurements. As you can see, this is how this one sets up. You have the sense resistor placed in between the source and the load, so then it will measure based on that. The advantage of this is it can trigger necessary action, so in case you do have an overcurrent situation, it can see that before it ever hits the load, and it can trigger like the switch or whatever, so you can cut power to the load before it ever destroys it. And it also doesn't add any disturbances to ground like low side current measurements would. The disadvantages to traditional high side measurements is that if you were to use a differential amplifier, it requires very careful resistor matching. If you are off by 0.1% of the two resistors, it will drop the counter mode rejection ratio of your amplifier to 46 dB from about 90 something dB, depending on your op amp. This is eliminated with the use of the current shunt monitor, since it puts carefully matched resistors in the IC already. So here's a current shunt resistor. This is the TI INA138. As you can see, it takes power from the battery here. It's taking a high side measurement across the sense resistor. The current's going to go through here, and then it's going to measure the voltage drop across that. And based on that, it's going to output this. This is actually a current outputting device. So this one, you need to put an extra resistor here, and it will give you a signal based on that current. And then from there, you can either process it with a microcontroller or even just pump it into a comparator and tell. So you can use it to control a switch or whatever to control current to the load. See what happens. This is low side measurements. The sense resistor here is placed between the load and ground. The advantage of this is that it's simple and low cost. You can easily play it. You can easily just use an op amp. You don't have to worry about resistor matching or anything. It's also the most accurate mode of current sensing, since you know what exactly is going through the load. The disadvantage of this is that it adds unnecessary resistance in your ground path. It can also, the circuit faults, if you were to have an overcurrent situation, it would go through the load before your device ever senses that there's too much current. And also, since it measures current to the load, you can't use it, current to ground, you can't use it in an antenna application. This is a operational amplifier hooked up in a low side. Here's the load, and here's your low side sense resistor, and this is measuring the drop across that resistor, and then pumping it to an analog to digital converter, which then goes to the microcontroller. This would be useful in like power management applications, since it's more accurate. And it's fun. And next, Kenji's going to talk about challenges.